Welcome. Let's take a look at what the derivatives can tell us about an increasing or decreasing function. We have a function here in our graph that is increasing and decreasing on various intervals. So we'll look at the interval from negative infinity to A to B, B to C, C to D, and then D on towards positive infinity. Now, we want to focus on what the derivative can tell us. So let's first observe about the differentiability of this particular function. As I look at this function, I can see that it is nice and smooth. There's no jumps or gaps. There's a single cusp here at x equals a. So my function is differentiable provided that x does not equal a. So we can talk about the derivative between negative infinity and a of the function, and we can talk about the derivative of the function from a onto b, but we cannot talk about the derivative at a. In fact, what we would say is that f prime at a does not exist. Now let's go ahead and think about what is happening between negative infinity and a in terms of the derivative. And it's probably easiest to think of this in terms of the slopes of the tangent line to the curve. So if I imagine drawing tangent lines to the curve along this segment of the function, what do you notice about those tangent lines? Well, all of the tangent lines have a positive slope. So we could say from negative infinity up to a that the derivative in that interval is positive because we can see that the slopes of the tangent lines in that interval would also be positive. Now let's consider from A to B. And let's consider again, imagine drawing tangent lines and thinking about the slopes of those tangent lines as we traverse the interval from A to B. Now what we can see is that all of those slopes are negative, so the derivative is negative in that interval. However, the magnitude of those slopes is getting smaller and smaller. Notice that the tangent lines are approaching the horizontal. And as they approach the horizontal, we can see that at B, we would actually have a horizontal tangent line. So that would mean that f prime at B is equal to 0. Now continuing along, we can imagine slopes of tangent lines from B to C. So imagine drawing those in, and we can see that they are positive. So the slopes of the tangent lines are positive, meaning that the derivative in that interval from B to C is also positive. We get to the point C, and we can see that this curve kind of flattens out at C, and we have a horizontal tangent line. So we would say that f prime at C is equal to 0. Continuing on, we can see that horizontal tangent lines in this next interval from C to D would all be positive, and notice that they're starting to flatten out as we reach x equals D. And at x equals D, we would see that the derivative f prime at d is equal to 0. Then continuing on, d to infinity, we can see that the slopes of those tangent lines are negative, meaning that the derivative in that interval is negative. So f prime of x is negative, and I neglected to write that f prime of x was positive in the interval from c to d. So let's go ahead and kind of take a step back and notice a couple of things. First of all, notice that when my function is increasing, so negative infinity to a, from b to c, and then from c to d, notice that in those locations, the derivative is positive. Now note that when our function is decreasing, so on the interval from a to b, and the interval from d onward to infinity, that our function is decreasing and that our derivative is negative in those intervals. Another thing to notice is where there is a change in increasing to decreasing. We see a change here at a, and notice what's going on with the function at a. The derivative at a does not exist. We see a change in increasing to decreasing at b. And notice what's going on there. F prime at b equals 0 is what's happening there. And then continuing on, we can see a change from increasing to decreasing occurring at d. And note that f prime at d is equal to 0. So what we can say is that a function changes from increasing to decreasing where the derivative either does not exist, in the case here a cusp, so where the derivative does not exist, or where the derivative equals 0. Now those points have a name. These points, x equals a, x equals b, and x equals d, are called critical points. So a function can change from increasing to decreasing or vice versa at critical points. Notice though that it doesn't have to change, that at a critical point the function may be increasing to the left and increasing to the right. But if I'm looking for intervals on which a function is increasing or decreasing, critical points are going to be crucial. And then checking the sign of the derivative on the corresponding intervals will help us determine that behavior. So now that we kind of see this connection between critical points and increasing and decreasing behavior, we're going to then use that knowledge to help us devise a means by which we can determine whether there is a relative maximum or a relative minimum of the function at the point. So let's start with our critical point A. And what do we notice? Well, f prime at A does not exist. That's how we know it's a critical point. We know that for x less than A, f prime of x is positive, so the function is increasing. And then for x between a and b, so a less than or equal, a less than x less than b, f prime of x is decreasing. So if we look at our graph, we have an increasing behavior followed by decreasing behavior. This at a critical point. If this occurs, if there's increasing behavior to the left of the critical point and decreasing behavior to the right, that implies that there is a relative maximum at x equals a. Let's look at critical point x equals b. So we know that b is a critical point because the derivative is 0. And we can say that for x between a and b, our derivative is negative. And we can say that for values of x between b and c, so between b and c, our derivative is positive. So our critical point is at b. To the left of b, we have decreasing behavior. To the right of b, we have increasing behavior. This tells us that we have a relative minimum at x equals b. Our next critical point is x equals c. And we know this is a critical point because f prime at c equals 0. And we can say that for values of x between b and c, that our derivative is positive. And then for values between c and d, our derivative is positive as well. So what does that mean? That means that we have increasing behavior to the left of c, and we also have increasing behavior to the right of c. So there is no relative maximum or minimum at c. So no max or min at x equals c. Now our last critical point is here at d. So at x equals d, we know this is a critical point because f prime at d equals 0. And so for the interval to the left of d, so that would be c less than x less than d, we can see that our derivative is positive. And then for the interval for x greater than d, we can see that our derivative is negative. So here's d, and we have increasing behavior to the left of f at d and decreasing behavior to the right of f at d. This tells us that there is a relative max at x equals d. So we can summarize what we just saw in the first derivative test. If we have a continuous function on an interval, and that interval contains a critical point c, and f of x is differentiable on that interval, except possibly at a point c, then f of c will satisfy one of the three conditions. So f prime of x is positive to the left of c, meaning f is increasing to the left of c, and f prime of x is negative to the right of c, meaning f is decreasing to the right of c, then f at c is a local maximum. Or f prime of x is negative to the left of c, meaning f is decreasing to the left of c, and f prime of x is positive to the right of c, meaning that the function is increasing to the right of c, then f of c will be a local minimum for the function. The last possibility is that f prime of x has the same sign to the left of c and to the right of c. So it could be increasing to the left of c and increasing to the right of c. Or it might be decreasing to the left of c and decreasing to the right of c. In this case, then f of c is neither a local maximum or a local minimum for the function. I hope you find this helpful.